Swayam Prabha. Digital India. Educated India.
Ramakrishna said, I am half of him, I am only Krishna. And I'll be talking about optimizations to start with, then focus a bit more on high-level optimizations. We'll explain what they are. See, I have a kind of weakness. I can teach when people talk. Okay. Talk to me, I talk to the class. So we'll try to keep the class as interactive as possible. If you have any questions, just unmute and speak. Okay, no hesitation whatsoever. No question is kind of weak or poor or anything of that sort. There is no silly question. There is no super smart question. All questions are questions. They are all good questions, and we want to hear them. Okay. If it was a real class, I mean physical class, I even go to the extent of giving chocolates when people ask questions. Okay, but here we cannot give you chocolates. But yeah, sure. Do ask as many questions as you want. If you have doubts, even if you think, hey, I have an interesting point to make, please interrupt and say. Okay. We'll start then. My name is Krishna, and if you want to reach me anytime, this is my email ID. Okay. We will start with an introduction to optimizations. Then we will go into loop transformations, and then we will work on optimizing function calls. Okay. Many of these slides are taken from Tony Hosking, who is currently at Australia. Okay. See, when we talk about compilers, it's one of those core subjects in computer science where you will find a sangam of all the CS fields. Algorithms, theory, systems, architecture, optimizations, artificial intelligence, machine learning, pick your choice. Okay. I mean, if you see the computer systems, if you divide three, kind of four main columns, right? You will have languages, compilers, architecture, operating system. You take away any one of them, the computer systems cannot stand, right? And we are here, we will be working in compilers. And we will naturally be touching upon few other topics as and when things are required. Okay. So if you like CS as a whole, you will love compilers. Okay. It has an extremely healthy mix of theory and practice. Traditionally, I mean, a compiler, you'll see, can be seen as a black box, which takes a source code and source code as input and gives us output machine code or some other code in some other language. Okay. You have...
for me also, sir, I think the presentation isn't rendering properly.
The presentation is not being rendered properly.
I also felt that.
All right. Which, do you see slide 6 now or not yet?
Yeah, yes, slides are coming, but sometimes it is overlapped. Like source code was in the front and everything was in back. So the pieces are visible and overlapped kind of. But now it is completely coming. I can see the full slide just now, but in transition, I see some problems.
Okay.
Yes, sir. Whenever you're changing the slides, they get overlapped.
Okay. I'll wait for it. Thank you. Yeah, so I have seen this happening with Google Meet before. We'll kind of wait at the transition. Okay. Thanks, Hari and Rajneesh. All right. So from the source code, when we go to machine code or whichever target language, invariably this happens in multiple steps. And we take if you want to look at it as a two-pass thing, right? You have front end that does the parsing, etc., gives you an IR, and this IR is fed to the back end. The front end maps legal code to IR. The back end maps IR to target machine. The IR simplifies retargeting many times. It can allow multiple front ends, and the back end can do multiple passes to generate better code. Okay. A rough statement is that most of the problems in the front end are simple or have been more or less solved to our satisfaction. And most problems in the backend are harder. Some are undecidable, some are NP complete in nature. And most of the research is going in this part. Okay. Our focus is a tiny part of the backend. If you look at a classical 7-phase compiler, right? The front end goes all the way till here, which generates the IR, or sometimes people will keep the front end till here. And then you have machine independent optimizations, code generation, machine dependent optimization. Okay. The front end recognizes syntactical tokens, finds that the code is syntactically correct. It recognizes legally correct code, reports errors, produces IR. Backend does the optimization. Our target is 1 out of the 7, mainly this part. Today, in the other lectures, you will cover other things. Okay. We may touch upon the other things based on me. Again, our goal is high-level optimization. Okay. When we say optimize, what do we want to do? I mean, we want to optimize it for what? Can someone tell?
For better performance.
Meenakshi says for better performance. Can you define what do you mean by better performance, Meenakshi?
As in vis-a-vis, if I do a comparison between, let's say, two solutions to the same problem, this one either has a better time complexity or a better space complexity, or it gives me some function which I want to optimize.
Aha. So Meenakshi says time complexity or space complexity. See, it so turns out. Okay, are there any other answers? Pavan says, I think the presentation will be smoother. Let me check what you're saying. If the incoming video is turned off, I can do that and see if that helps. Okay. My guess is that it's not to do with the video, but some issue with the screen sharing that Google Meet involves. But fine, we'll see. Yeah, so Meenakshi said it can reduce the time complexity. Anything else, guys? Any other answers? Now? All right. See, Meenakshi, when we say it should produce, it should optimize, reducing the time complexity is one step too far away. We are happy if it reduces time, execution time, even if the complexity doesn't change. We are happy if it reduces the memory requirement, even if the space complexity doesn't change. Okay. There are other factors also we may care for. Time, space, energy. There are many such factors, power. And we are not talking about optimum code. Okay. We are not talking of the most optimum code. No. Many of the problems are hard here. Some are even undecidable. See, there are so many optimizations. Sometimes it's even a headache to find out which optimizations to use, because not all optimizations work well together, because they may overlap or interact. If you do A followed by B or B followed by A, I mean, where A and B are optimizations, you may get behavior which is kind of slightly unexpected or unwanted, right? Is the slide 9 visible?
Yes.
Yes, thank you. Yeah, see, when we say an optimization is a transformation that is expected to improve. Improve what? Some parameter that we care for. Could be the running time, could be improve the memory overhead, that is, reduce the memory space requirements. So what we are saying is improved, not optimal, not optimum. Sometimes it can also produce bad code. Okay. But our hope is that most of the time it should do well. The speed up could be some very little to some big factors of improvement. In general, it is undecidable whether a particular optimization will improve performance, always, or even most cases. It's difficult. I mean, these optimizations are not straightforward. So here is a fun question to start our day with. I mean, this is again asking this particular question. Is it really the case that we cannot really find out whether an optimization will always improve the performance? Let us say I am doing A equal to A times 2. Okay. I replace it with A equal to A left shift 1, because you know that left shift is faster than multiplication. Okay. Or instead of 2, if you like it as 32, make it left shift 5. Okay. So here is the question: is it guaranteed that this optimization will always improve performance, or is there a chance that even such an optimization can lead to worse performance? Any thoughts?
After doing this optimization, you lose out on other optimizations that could have happened, but now you can't do because of the left shift.
Yeah, I mean, there may be another optimization that I'm doing that, yeah, very good. I like Rupanshu, right? Rupanshu's answer. Let us see the code looks like this. The code was A equal to A times 32, followed by plus 5.
What you are writing on the whiteboard is not visible. I don't know whether that's a problem with me only or with everybody else.
Oh, you're not able to see the whiteboard?
No, the text on the whiteboard is not visible.
It would be visible when you'd share like your desktop.
I've
Probably
shared the desktop, dear.
when we just share some
I have shared
particular application.
No, I have actually stopped. I have shared the full desktop. Let me share it again. Let me stop sharing and start again. Yeah. Let us say the original code was this plus this. Okay. Or let me make it this way. Yeah. And there is some instruction called, let's say I have A equal to A times 2 and A equal to A plus 5. There used to be an instruction called multiply by 2 and add. So mul add. The instruction name used to be mul by 2 and add. So if you have these two instructions, maybe I may be able to do these two together using an efficient instruction called mul to add. But if I first replace this with A equal to A left shift 1, I won't even do this transformation. Maybe it's not great. Maybe because of this transformation, some other instruction scheduling or some other optimization got negatively affected. Okay. So let's be aware that these optimizations are not God sent. It's difficult to argue that the optimization will always give me great results. Okay. Okay. So what we are saying is, in addition to this fact that different optimizations can be kind of interacting and interfering with each other, their goals can also be different. Their optimizations can be focused on speed, to improve the speed. There are optimizations that may be focusing on. Oh, wait. You still cannot see my screen, right? I've changed this. Now it came. Okay. Yeah, there are optimizations that improve speed. There are optimizations that improves memory. There are optimizations that improve power and so on. Okay. Which one matters? Can someone tell?
That would be context specific, right? Like if
Vishnu
you're
says
running,
context specific. What do you mean by context, Vishnu?
if you're running something where speed is the most important thing, you'd have to have your compilers working so that it runs faster even at the cost of power or space. But if you're trying to design something where power is, we are trying to conserve power, that would be the sort of compiler you'll be working.
Very good. Very good. So the point is, it depends. It depends on the target machine. It depends on the target application. It depends on the who is. I mean, what am I running? I mean, what I as the user want. Okay. You may ask, why should I worry about? Why don't I just do something that is fastest, best for memory, best for power, best for energy, smallest size code, and so on, right? Why not get all? It so turns out sometimes improving one will negatively impact the other. You improve one, the other one goes for returns. Okay. Traditionally, the compilers have targeted the speed of the generated code. Okay. Sometimes size of the code as well, but mainly the target speed. Okay. Sometimes improving the speed can improve the size of the code as well. Sometimes improving the speed will not decrease the code size, but instead increase the code size. I mean, here is an interesting example. Let us say I have a loop. I equal to 1 to 100. Let me write the other way. Between these two codes, what's the difference between the code 1 and code 2? Anyone?
+1 and +2.
Loop unrolling.
Right. So what I'm doing is I have unrolled this loop. Here in each iteration, I was executing one instance of the body S. In each iteration here, I'm executing two instances of the body S. What's the advantage or disadvantage of C1? I mean C2 over C1.
You have to do the check less in C2. I less than 100 will get checked lesser amount of times.
Okay.
And the increment is also done.
So I'm checking fewer number of times. I'm incrementing fewer number of times.
Yeah.
I'm jumping fewer number of times. Correct? So which code? Yeah, go ahead. Meenakshi, you're saying something.
Yeah. The step size has caused the optimization here, increment in step size. So instead of +1, it's +2, which has caused the code to optimize.
Correct. So which is better, C1 or C2? Which code is better? Vishnu, so can you define dependent?
If S itself is
Sindhur Anjuman said Tej. Should we call you Tej or Sindhur Anjuman?
it's
Sindhur, yeah. So Sindhur says depends on the complexity of S. Can both of you explain what you mean by your statements? Sindhur, Tufan.
If S itself is very complex and dependent on I, and there's a lot of changes in S, so when you write S again and again, it'll just make the performance worse.
Why?
um,
How will-
unrolling it and then running it would just at that point changing the value of I or the checking, those are less costly than SS. So when you unroll S and do it twice, you'd be actually spending more resources there.
More resources. You're using too many. You're using a lot of words. Let's be careful. Let's use them. What's the right word? Being aware of the words. Okay. So what happens when I write code like C2 instead of C1? Am I doing more work or less work?
You're doing pretty much the same work, but
are you doing the same? Okay, fine. Let me ask three. There are three options: same work, less work, or more work.
Depends, I guess. I'm not sure.
Or Sindur says if S has high complexity, the unrolling is not really doing much. Why is that so, Sindur? Am I reducing the? See, there are three things that have changed. I'm comparing fewer number of times. I'm incrementing fewer number of times. I'm jumping. I have fewer number of branches. So how is it? How is the complexity of S impacting on the work done by C2 or C1? Let's ask ourselves this question: is the complexity of this code changing? C1 and C2, is the complexity same? Meenakshi? Or is it different? Sindur, is the complexity of C2 different from C1? Instead of 100, let us make it sum 2n, okay? If the complexity of S is some function f, okay, then the complexity of C1 is order of n f, correct? Some function f. I'm skipping the details. What is the complexity of C2? It is still the same, order f. So the complexity has not changed.
Same, it will be same.
Correct. So whether S has high complexity, low complexity, the work done in C2 is less or more? That's the question I'm asking.
It should be less, like the work done in C2, since we are doing less comparisons and less jumps based on that.
Less comparisons, less jumps, less fewer increments.
Yeah.
Fewer jumps, fewer comparisons, fewer jumps, right? So is C2 better than C1? We are again coming back to the same question.
So what if the iterations are dependent on each other? Like previous iterations values are needed for the next iteration. This won't be possible, right?
Previous iteration?
Like we are taking an iteration number n plus 1, and this n plus 1th iteration need values from nth iteration, like take accumulation, for example.
Which is perfectly fine, right? I have not changed the order of the execution anywhere, right? If let's say that initially I was executing S0 followed by S1 followed by S2, where S0 means S with I equal to 0, and so on till S99. Here also I'm doing the same order, right? S0, S1, S2, S3, so on till S98, S99. No difference.
Yes, so makes sense.
So semantically they are equivalent, no doubt about it.
Yeah, they are equivalent, and less work should be run in every case, I think. For C2.
All right, so C2 does less work. That we have established. The question is, and let's assume that in S I do not modify I, okay? Let's assume within S I do not modify I. That's a requirement. But we will not worry about it for the time being. So we have established that C2 does less work than C1. The question is C2 better than C1?
C2 is better in terms of performance, but let's say if we want to flash this code on an embedded device which has less memory, then C2 will take more memory. And in that area, we will say that C2 is not better than C1.
All right. So we have a few answers on the chat window as well. It says work done is less, but complexity is more. Yes. Complexity is same, work done is less. Yes. Yes. Pawan is saying like what our friend just said, that the code size is more. So if my target is to reduce the code size, then C2 is not a great idea. Let me ask you a question. Let us say my target is to reduce the speed. Is C2 better than C1?
Not necessarily, because like you might have some cache effects of writing S twice, and S might be going out of cache and then you bring it in back again, something.
Rupanshu says there may be some cache effects. Yeah, Rupanshu, can you make it slightly more specific?
So let's say when you execute the first S, in the C1 case, you jump back to the beginning of S, and that might still be in cache.
What might be still in cache?
Like whatever S access is there, or like maybe the instructions.
No, let's see again. Let's be aware of the words they are using. I'm not sure if you realized you used two words and they are different. Whatever, let us say this S consists of many instructions. Okay, I1 to I10, let us say. Okay, you said what I1 accesses and the instruction I1. Which one you are referring to? Let's be aware that they are different.
I think we would need like I1 to be in cache. I don't think it matters if the thing I1 accesses is in cache or not, because the other S might access something different. So I think the instruction matters here.
Very good. So the point is here, when after I have executed these 10 instructions, I'll get back to the same first instruction. These instructions, where are they fetched from? Can someone tell? Where are they fetched from?
Memory.
Memory. And we don't always fetch directly from memory. We bring from memory to
instruction cache.
Cache. Very good. Very good. See, maybe in my I cache, all the 10 instructions of S may fit. Okay, if all the instructions of S may fit within my I cache, then perfect. I'm always within my cache. But let us say 20 instructions don't fit in my I cache. Then what will happen when I go to the second part and come back to the first? Few instructions have been evicted from my I cache. As a result, there is more memory accesses. The number of accesses is more. So C2 becomes worse. Do you see how such a seemingly simple optimization, how it is impacting the performance? I hope this excites you that, wow, this is non-trivial. Any questions so far?
So this basically says that for any kind of optimization, we can't be sure if it will help with the performance or not. It will always be like
yes,
question on that.
Jasmine, what I will do, I will take your words and rephrase them slightly. I will tell, for any optimization, we want to apply if we have high confidence that it will improve performance. Okay?
Yes, I think so.
Not 100% confidence, reasonably high confidence. Okay? Or sometimes just confidence, even if not high confidence. See, there are other things that may happen, not just iCache in this loop unrolling. Your code size is increased. You will learn about register allocation. If you do unrolling, the register allocation, you may need more registers. You may put more things in memory. So, lot of things change. So you have a series of optimizations, and they interdepend. They are all interdependent. Many of them are. Okay.